So our next speaker is Jeffrey Duperret from University of Pennsylvania. And cue screen. Right.
All right. Hi, everybody. My name is Jeff Duperret. I'm a PhD student with Dan Kodacek at the University of Pennsylvania. And I'll be talking about my work with the Inu robot, which is a quadrupedal platform built to test hypotheses regarding the presence of a spine morphology for legged locomotion. So while mammals have been documented to use their core muscles to increase their locomotion prowess, very little experimental investigation has been done into the benefits of robotic core actuation. So Inu's spine consists of one actuated degree of freedom in parallel with a compliant fiberglass leaf spring. Motors in the rear body segment of the robot act on a sprocket that drives a belt to give the spine a pitching degree of freedom. And the vertebrae you see between the belt and the fiberglass leaf spring constrain the bending curvature. So we can use fiberglass leaves of a variety of thicknesses to optimize for either storing elastic potential energy or allowing the motors to bend the spine through its full range of motion. So we've learned a lot regarding this morphology. Today I'll be going over 3 documented advantages of integrating this mechanism onto quadrupedal platforms for non-steady state tasks. So the first is that the rapid release of stored elastic energy in the spine mechanism can accord specific leaping abilities beyond what the motors are capable of alone. So this video is actually work on Inu's predecessor, the canid robot, but the spine mechanism is very similar. So what the robot is doing here is compressing a rather thick fiberglass leaf spring and then rapidly catapulting itself by releasing this energy. I'll run it again. And the spine motors extend in parallel with the elastic energy release to get the benefit of both the elasticity and the motors. So yeah, in this work we showed that the robot was able to achieve greater specific agility or mass-specific work generated in a single stride, much beyond what the motors were able to produce alone. And indeed, this robot can leap about a meter, which is double the distance of its rigid-back cousin Rex, even when Rex uses more motors. So we're definitely getting a benefit from this stored elastic energy. The second benefit is there is quantifiable added volumetric workspace provided by the spine bending. So this is important because as legged robot designers, we always face a trade-off between increasing the leg length to increase the workspace of the legs, or decreasing the leg length to increase the force generation for the legs. And the spine actually allows us to circumvent this trade-off by augmenting the leg's workspace without increasing its leg length to decrease its force affordance. So an example of a task where this makes a difference is that the Inu robot is able to perch on and move off of an isolated foothold, which is, kind of the prototypical task for unstructured environments that we want to be able to accomplish with robots. And we can show whereas if the back was rigid, this would be impossible if the given kinematics. So, and then the third benefit applies to otherwise direct drive robots. There's an emerging trend in legged robotics right now to build direct drive machines, which is no gearboxes between the leg and the motor, as opposed to gearing the leg motors. So one advantage of direct drive is the ability to sense environmental contact at high bandwidth using motor encoders as sensors alone, but the disadvantage is you incur the obvious force production penalty. So, but by gearing the spine, we can provide greater motor energy output per stride than the legs can, while losing no environmental fidelity. So it's a pretty simple calculation to show that the specific work benefit of the geared spine motors can be greater than that of the direct drive legs, making the spine worth its added weight in this sense. So there's no spring compliance or elastic energy storage in the spine right now, and it can leap much further with the spine. And of course, all 3 of these benefits come at the cost of added weight and complexity. We hope that by quantifying them, we can let designers decide for themselves when the spine is the appropriate morphology. So going forward, there's still a lot of untested hypotheses, and right now we're looking at steady state locomotion. And work is in progress to analytically show stability of Inu's closed loop bounding controller. we anticipate a speed benefit incurred by the added stride length. And we also hope to show that there's an increase in energetic efficiency by storing and releasing energy on each stride. So thanks, and I'd love to take any questions.
Questions? You see one from Jason back there?
I get the first two of your benefits. I don't get the third one because if you have a direct drive motor, you're burning a lot of power just to generate the torque. You might as well spin it as fast as possible to get the power output at the same time. So what benefit are you getting by having a second motor doing the same redundant work?
So yeah, that's a great question. So when you're in stance, and let's say you're pushing off, the amount of force or the amount of work you can generate in stance is your torque multiplied by the angular rotation that the motor goes through. So with direct drive motors, you're never really on the speed. You're always near your stall torque. So you can pretty easily calculate the work a leg motor can do. If you gear the spine, you are multiplying that work production by the spine gearing. So as far as like leaping as far as you can, you get the angular rotation times the stall torque times the gearing, and so you generate much more work in stance than you would with a leg motor, if that makes sense. Another way to think about it is you can just generate much higher forces with a geared mechanism versus a direct drive.
I'm imagining that they're in series, so I'm not sure how you're getting greater. Maybe I'm not. Maybe.
Yeah, they are in series, and yeah, I guess the dirty secret here is the leg needs to be near singularity to transmit those forces by the spine, and that's what we do when we leap with our robot.
Okay, excellent. Thank you very much.
Thanks.